Okay, so picture this, Europe, right? And it's in the grip of this just incredibly harsh 70-year freeze. We're talking roughly 1645 to
Yeah.
1715.
A really tough time.
Rivers frozen solid, harvests failing constantly. Just, well, unimaginable hardship. That's the Maunder minimum period.
Mm.
But here's the really weird part, the twist. During that exact same time, sunspots, the dark patches on the sun,
Gone, pretty much.
they basically vanished. And this surprising link, it was really brought into focus by the U.S. astronomer Jack Eddy back in 1976.
Right, building on work by Maunder himself and Spörer even earlier.
Exactly. So it
Yeah.
immediately makes you wonder, okay, is this just a massive coincidence or is there something really going on here?
Absolutely. And that's precisely the puzzle we're diving into today, based on the great material you sent over, exploring this whole intersection. What's happening with our star and how it hits us here on Earth.
Yeah, it's fascinating stuff.
So for this deep dive, we're going to consciously set aside the more recent climate change drivers everyone talks about.
Right, and things like El Niño, volcanoes, the usual suspects.
Exactly. We want to really zero in on these, let's say, longer-term astronomical connections that your sources highlight.
Okay, got it. So we have this cold spell, we have the missing sunspots. It's an intriguing puzzle. Where do we start pulling on the threads? What's the path here?
Well, I think it makes sense to start with this sort of uh, more established astronomical factors that influence Earth's climate, things we have a pretty good handle on.
Like what, for instance?
Think about the Milankovitch cycles, these really long-term shifts in Earth's orbit, its tilt.
Oh, yeah, the things driving ice ages over millennia.
Precisely. They're fundamental. We can also touch briefly on polar motion, that slight wobble of the Earth's axis. Minor, but part of the picture.
Okay, the established cycles. Then what?
Then we can, zoom way out, think geological time. Your sources mention possibilities like our solar system drifting through giant interstellar clouds of gas and dust.
Wow, okay. That's big picture.
Huge picture. Or even gravitational nudges from the Oort cloud way out there, or perhaps even our path through the Milky Way spiral arms, affecting things over vast, vast timescales.
Right, the truly cosmic influences. And then we come back closer to home, back to the sun.
Exactly. Then we bring the focus right back to our own star and its, let's say, more dynamic, shorter-term behavior.
Okay.
So we'll look at things like its rotation roughly 27 days, and the big one, the 11-year cycle, where its magnetic poles completely flip.
And the sunspots are tied into that cycle, aren't they?
They absolutely are. Sunspots are a key visual indicator of the sun's magnetic activity, and this is where we really dive deep into the Maunder minimum.
That's 1645, 1715 period again?
Yes, and also an earlier one, the Spörer minimum. Both of these periods lined up pretty neatly with the coldest chunks of what historians call the Little Ice Age.
Okay, so multiple instances of low sunspots matching cold periods.
Correct. And just for balance, we should probably also mention there were warmer periods too, like the medieval maximum when solar activity seems to have been higher.
Right, got it. So the timing lines up, we see these correlations, but what are the theories for how less activity on the sun could actually cause colder weather here? What's the proposed mechanism?
Well, that is the million-dollar question, isn't it? And there isn't one single universally agreed upon answer, but there are some really compelling hypotheses that your sources touch on.
Okay, like what?
One major line of thought involves the solar wind. That constant stream of charged particles flowing out from the sun.
Sure.
When the sun's more active, the solar wind is stronger, more turbulent. It actually provides a better magnetic shield for the inner solar system, deflecting some of those high-energy galactic cosmic rays coming from deep space.
Okay, so a strong sun means fewer cosmic rays get through.
Exactly. Now, the hypothesis goes, when the sun is quiet, like during the Maunder minimum, that shield weakens. More cosmic rays penetrate Earth's atmosphere.
Right, and what do the cosmic rays do?
Well, the idea is that these cosmic rays, as they hit the atmosphere, can create ions, charged particles, particularly in the lower atmosphere. And these ions might act as sort of seeds, condensation nuclei, for cloud formation.
Ah, okay. So weak sun, more cosmic rays, potentially more clouds.
That's the proposed link. More low-level clouds could reflect more sunlight back into space, leading to a net cooling effect on the planet. It's quite an indirect mechanism, but fascinating.
It really is. Are there other ideas too?
Yes, there's also the direct impact of the sun's total energy output, the total solar irradiance, or TSI. It does vary slightly with the 11-year cycle, but the changes are generally thought to be quite small, maybe too small on their own to explain the Little Ice Age. but perhaps they play a role in shifting atmospheric circulation patterns.
Like changing jet streams or something?
Potentially, yes, shifting where the heat gets distributed. And we should also remember, as your sources note, that increased volcanic activity was likely also a factor during parts of the Little Ice Age. Volcanic aerosols block sunlight, too.
So it might be a combination of factors.
It very likely is. Nature is rarely simple. But what's really interesting, and adds weight to the solar connection, is that climate models have been run trying to simulate that Maunder minimum period. And they've actually had quite a bit of success reproducing the kind of cooling seen in the Northern Hemisphere, primarily by tweaking the solar input, even by small amounts, suggesting it can significantly alter atmospheric patterns.
Wow. Okay, so the models support the idea that even subtle solar changes can have a noticeable climate effect.
Yeah.
Yeah, that's powerful.
It lends credibility, definitely.
And you mentioned looking back in time, your sources talked about using things like ice cores and tree rings to figure out past solar activity.
That's right. It's ingenious, really.
Hmm.
Scientists analyze isotopes like carbon-14 found in tree rings and beryllium-10 in ice cores.
How does that tell us about the sun?
Well, these isotopes, they're called cosmogenic radioisotopes, are created when those galactic cosmic rays we talked about smash into atoms in our upper atmosphere.
Ah, the cosmic ray connection again.
Exactly. So when the sun's quiet and its shield is weak, more cosmic rays get in, meaning more carbon-14 and beryllium-10 are produced. This gets incorporated into tree rings as they grow or trapped in layers of ice.
So we can drill down through ice or count tree rings and measure these isotopes to get a timeline of cosmic ray intensity, which tells us about past solar activity.
Precisely. It gives us a proxy record stretching back centuries, even millennia. And looking at this data, scientists see these grand minima like Maunder and Spörer popping up.
Are they regular? Like clockwork?
It doesn't seem like it. The analysis suggests these events, where solar activity stays really low for decades, aren't strictly periodic. They seem to occur somewhat, well, unpredictably. But the data does hint that the unusually high solar activity we've seen in recent decades might be sort of winding down later this century.
Winding down, meaning we could potentially be heading towards another period of low activity, maybe even another grand minimum like Maunder.
It's certainly within the realm of possibility based on these long-term reconstructions. The sun's done it before.
Which naturally leads to thinking, is our sun weird? Or is this kind of up and down, sometimes really quiet behavior normal for stars like ours?
That's a fantastic question and a real challenge. Obviously, we can't directly check our sun's tree rings from a million years ago.
Right, so how do we know if these minima are common?
This is where studying other stars becomes incredibly valuable. Missions like the ESA's Hipparcos satellite, and especially now Gaia.
Gaia, the one mapping billions of stars.
That's the one. Instead of just relying on our sun's limited historical record, we can look at thousands, even millions, of other stars out there that are broadly similar to our sun.
How do you define similar?
We look for stars with similar mass, age, temperature, chemical composition, rotation rate, basically sun-like stars. Then we measure their current magnetic activity levels.
Okay.
And the logic is if we find, say, 10% or 20% of these sun-like stars are currently in a state of very low magnetic activity, looking like our sun did during the Maunder minimum.
Then that suggests it's a relatively common phase for stars like ours to go through.
Exactly. It gives us a statistical baseline. Early surveys gave different estimates, but the approach is powerful. We're essentially using snapshots of other stars today to understand the potential long-term behavior, the life story of our own sun.
It really puts our star and our moment in time into a much bigger cosmic context.
It absolutely does.
So for everyone listening, chewing on all this, the big questions that jump out from the sources are things like, was that really intense cold during the Maunder minimum actually caused by the sunspots disappearing?
The causality question.
Yeah. And does the sun's activity, its ups and downs, have a truly significant, measurable impact on our climate beyond just the obvious seasonal changes?
How strong is the link, really?
Right. And these big lulls, these grand minima, are they just random blips, or is there some deeper cycle we just haven't figured out yet?
Predictable or chaotic?
And maybe the biggest one, is our sun now, its current activity level, actually normal for a star its age? Or is it maybe a bit unusual? Lots to think about there.
Definitely. And just to sort of wrap up the journey we took, we explored this really intriguing connection, didn't we?
Yeah.
Between solar activity, especially these periods like the Maunder and Spörer minimums, where sunspots virtually vanished in colder times on Earth, like the Little Ice Age.
Yeah, and we saw evidence popping up from lots of different places.
Exactly. Historical records of people actually looking at the sun, records of auroras, which are linked to solar activity, then the clever science using carbon-14 in tree rings, beryllium-10 in ice cores.
And even looking outwards at other sun-like stars.
Precisely. Studying stellar analogs.
So for the listener, I think the key takeaway is that even though the exact way it works, the specific mechanisms linking the sun to climate are still debated.
Right, that cosmic ray and cloud idea is a strong contender, but still under investigation.
The correlation itself between low solar activity and colder spells seems pretty robust historically. And the fact that climate models can actually reproduce some effects of the Maunder minimum adds weight to it.
It suggests a real physical influence even if the details are complex.
And crucially, the possibility of another grand minimum happening, maybe this century, is on the table based on the long-term data. Plus, we're getting better context from missions like Gaia, figuring out if our sun's behavior is par for the course.
Absolutely. And if we can connect this back to why understanding this matters, well, getting a handle on these long-term natural climate swings provides really vital context for today's discussions about anthropogenic climate change.
Yeah, it helps build a more complete picture, doesn't it? It shows that climate is shaped by multiple forces operating on different timescales.
Exactly. Natural cycles, human impacts, they all weave together. Understanding the natural baseline helps us better understand the changes happening now.
Okay, so here's a final thought to leave everyone mulling over. If the historical record suggests these periods of a quiet sun coincided with colder times, what might happen if we do enter another grand minimum in the coming decades? But this time, in a world that's already warming rapidly because of human activity.
That's a really interesting point. How would those two forces interact?
Could a natural cooling cycle partially offset the warming? Or would they interact in completely unexpected ways? It really pushes you to think about the complex dance between natural drivers and human-caused changes shaping our planet's future climate.